Hello, my name is Kayhan Batmanghelich. I'm an incoming professor in electrical engineering department. So I view the application of AI in medicine into 4 quadrants based on their application in bedside practice or their involvement in medical research, and whether they are more heavy on the method development, algorithm development, or they're more concerned about practical application. So I'm going to talk about 4 projects in 4 quadrants very briefly. If we are interested in the application of AI in bedside practice, we have to be very concerned about the underlying biases that might be hidden in our model or in our data, because otherwise it can make the biases systematic in our healthcare system. So we realize that the current state of the art in model explainability mostly focus on where but not why. And as a result, we develop a model that is able to characterize the progression of the disease and explain the model using the progression of the disease and convey it to radiologists. It is also able to open these black boxes and convey the same concept with the same terminology that is used by radiologists, because at the end of the day, those are the ones that should be able to audit our model. So let me switch the gear and talk about another project that is mostly involved about the medical research. So decision-making in healthcare is always multimodal. Practitioners look into an array of information from images, EHR data, and lab tests. Now imagine that you have developed new biomarkers and you want to relate it to other modalities, for example, measurements from the blood. Usually these problems is cast as a hypothesis testing, and the power of such a test is governed by the number of the patients that have both modalities. But in the real practice, this is the case that you have, that although you have a set at both modalities, you have a lot of data that there has a missing modalities. And this is the expensive data set typically discarded. So we develop a statistical model that can pave the way, we can take advantage of the data that is usually discarded by controlling better the false positive, also improving the power under some circumstances. Now, let me talk about another project. This is mostly on practical application of AI, again, for medical research. We have been working on a project to characterize a disease called non-alcoholic fatty liver disease, NAFLD, which is a liver disease that characterized as development of the stiffness of the liver. The current practice is like this, that there's a machine called magnetic resonance elastography that make a physical vibration over the body, and MR monitors the progression of this physical rate. However, this tool is not accessible across all medical centers. So we develop a machine learning method that uses normal MR machines without this MR specification and incorporate underlying physics in order to estimate the stiffness of the liver and make this model more accessible to our other places. And finally, let me talk about the last quadrant, which is mostly on the practical and deployment side. There is a procedure called carotid endotractotomy, which is a surgical procedure that, that opens the carotid vein to basically clean it up. Part of this procedure involves clotting the carotid, and so that the blood can come from the other vein in the back of the neck. However, this is very risky procedure, can result in ischemia, and ischemia can result in a stroke. And in fact, 3 million people are quite at the risk of the stroke on this specific surgery and many other surgeries. The image that you see on the middle is my collaborator, neurologist collaborator that monitors the EEG signal to call the surgeon that the surgeon is at risk. We are developing a machine learning algorithm that monitors the EEG signals and to make this procedure more accessible, less error-prone, and more robust. And as a result, we can make it more accessible for many other places. Thank you.